Good morning, everyone. Good morning, esteemed participants, and welcome to the sixth day of our national level FDP on structural equation modeling with Amos and econometric analysis with EView. Your commitment to enhancing your knowledge and skills in the crucial area of research and analysis is truly inspiring. We had an incredible journey so far exploring Amos and transitioning to EViews expertise. Today, we have honored to have Dr. Ankit Saxena, Associate Professor at GLA University, Mathura, as our guide into the world of EViews and econometric analysis. Let us dive in the let's dive in and make today just as enriching as the ones before. Welcome on behalf of entire Kristu Jayanti family. A warm welcome to you, sir. We are delighted to have you here. Let us begin with today's section. Over to you, sir. Sir? Yeah, okay.
Yeah, thank you so much, ma'am, for the inaugural thing, and I will be starting discussion today. So yesterday we started the learning journey of the EViews basics, and we covered around a few things like a stationarity, how to develop a basic regression model. So we did all that thing yesterday. So today we'll be further going in some more important things that we can do in the EViews and how we should run and why and when these things are important. That's what we'll be capturing here. So one by one, some of the basics and very important tests, we'll be referring to, and then we'll start the understanding of those tests and when to use them and how to use it. So yesterday we actually talked about the stationarity, and just to recap quickly here, that stationarity is a very, very important concept. Reason being, if you wish to forecast any series, so you need to be sure about this assumption. And it's a basic assumption like the data that you are trying to forecast is actually, going to be in a way very much, stationary in nature. And how do you identify whether the data is actually stationary or not? So in general, I told you yesterday that my voice is coming clear to you. I'm actually using a different locations. I just wanted to confirm that. Is there any distortion coming to you?
Yes.
So I assume it's fine as of now. Thank you so much. So that way, the stationarity, we can address the problem of stationarity by checking few parameters. So if the mean, variance, and autocorrelations, if they remain constant over the time period, so then in that case, we normally make that thing that, okay, the stationarity is there. And there are various, statistical methods of establishing whether that data that we are trying to, build our forecasting model for is actually having that attribute of stationarity or not. So yesterday we saw the correlogram, that was a diagram of correlations. So autocorrelations and partial autocorrelation diagram we saw. And then we also saw the graph itself, which tells you about the range in which that particular variable is moving. And then obviously we could see the basic augmented decay Fuller test, and that helps you to decide whether your the data is carrying the unit root or not. So if the null hypothesis there was, I repeat, the null hypothesis was that the series that we are evaluating contains a unit root. That means non-stationarity. So ideally, the thumb rule is that we want that this particular hypothesis should be rejected so that we can establish that our data is stationary in nature. So what we did yesterday, we checked the stationarity on the concept of on the variable of closing values of one index, and then we also checked the stationarity of the return. So what we could understand that closing values were not found stationary, So they should not be made part of any analysis where you're trying to build a model which is trying to predict something. So that will not be a good idea. So because the stationarity is not there. So that stationarity could be found in the return data. So that return data could be used for making a prediction model, because then that prediction will be more accurate. So stationary time series is a very much important thing, and that's we have covered yesterday also. We did that analysis in the EViews itself. Now today we'll be discussing about some other basic things, and at the end, if time will permit, we'll talk about causality Granger and some Johansson integration test as well. Tomorrow we'll be going further deep diving in the further concepts of the EViews, and we'll be concluding the FDP that way. So today, let us understand. The first thing that we have tested is the stationarity. So the stationarity has been established. If in all the variables, then we can develop a regression model for those particular variables selected for the study. Now, another very important thing is about checking for the serial correlation. So in general, what happens? The assumptions of the regression requires that if there's a residual term in your data, that residual term of the data should have no autocorrelation. They should not be correlated to each other, and the residual, over the time, if we autocorrelate them, they should not have any correlation whatsoever. That is a very, very important thing. Just a minute. So eventually, this test is used. One more test that we'll discuss. The Durbin-Watson test is basically used for checking that particular thing, that whether the first order serial correlation or the autocorrelation in the residuals of the regression model. Now, what is the residual? Let me make you understand. When we work on a data set, so we have the actual values and we calculate the forecasted values of that particular data. So the difference between the forecasted value and the actual value is normally referred as the error term or the residual term. So these residual terms, ideally in ideal world, when they are squared, I told you yesterday, the least square method, what it does, it just calculate the error term and it squares the error term. So that's why the least square error is there. That's why we call that method, least square method. So you have a data set, let's say for last 15 years, you calculated the forecasted values. You can apply the regression on that data itself, and you can compare the difference between the actual values and the forecasted value. So you have the 15 years actual value. You can calculate the forecasted value using the forecasting model you have developed, and then you can take the difference of these two numbers. So if the actual values are too far from the forecasted value, obviously that shows that something is not correct with the forecasting model. And more or less, the residual that we are receiving, this should not be correlated. Like if every time your variable, that is increasing by a certain number, and your error also increases by that certain number, and this happens on and off again and again. So that means the residuals that we are getting in the model, in the forecasting that we are making, they are also getting correlated and auto-correlated with each other. And that is going to be a breach of assumptions of the forecasting. So we have to ensure that if we want to make sure that my regression model or the forecasting model is a valid and reliable forecasting model, I have to ensure that my autocorrelations of residuals in a regression model, they should be not significant. So ideally it should not be there, but even if it is there, it should be not significant. So the methodology for that particular thing is we calculate the Durbin-Watson statistics. I'll show you where to see that. And the normal range, we'll see for Durbin-Watson statistics going to be 0 to 4. And the value of midway, that is 2, indicates that there is no autocorrelation in the residual terms. If the values are less than 2, then we'll call it a positive autocorrelation. We have to be careful. Like if it is like 1.95, 1.96, or even 1.9 or 1.8. So it is, slightly deviating from the ideal value, but the positive autocorrelation may not be much significant. So we have to use further few more tests to deep dive into that thing. So a value close to 2, will indicate that there is no autocorrelation. So 2.01 and 1.99, we're close to that too. So you won't get perfect 2 every time, but if you're getting something near to 2, that will be a point to tell you that your residuals are not autocorrelated, which is a good thing. And if the values are slightly, let's say, towards the 0, or the values are slightly towards the 4, that tells you that some serious autocorrelation in the residual terms, and that way we need to use some residual diagnostic then, and then upgrade and modify our model and use the appropriate techniques which take care of such residuals that are causing an issue in our validity of the regression model. So I hope I'm making myself clear. Yesterday, we discussed about the stationarity. Today, what we are discussing, we are talking about the Durbin-Watson test, and we'll talk about one more test for that purpose. So, which basically captures the issue of this serial correlation. So, we are testing our data that whether our residuals are they correlated. These are the assumptions of regression. Normally, what happens? We normally ignore this part. So, what I normally believe and advise everyone that before conducting any analysis, you must go through the basic prerequisites and assumptions of that test, so that you know that exactly in regression there's a condition that where we are applying a regression, the autocorrelation of the error term should be 0 and they should not be correlated to each other. These are the assumptions of the regression. If you go through any good statistics books, the book that I've shared with you, you will find this particular thing mentioned in that thing as well. Diksha, I'll try to speak a bit louder. I'm not in the studio right now. Today I got that the studio was not actually open, so that's why. Is it coming better now? Okay, thank you so much. So I'll try to speak a bit louder so that you get that thing. Thank you so much. It's better to tell. I can try one thing. So let's try, and if that issue persists, please ping me 1 second. So the value of Durbin-Watson here, what we are getting, Durbin-Watson value is an indicator to tell you whether this autocorrelation of the residuals, is significantly creating an issue or not. So when I get Durbin-Watson value 0.5, or when I get Durbin-Watson value like 3.5 or 3.6 or close to 4, so it's a very clear picture that is telling me that my residuals, are having a serious autocorrelation. And then, working on a simple forecasting model without discounting the, this impact of autocorrelations that exist between the residual, will not be a good idea. So what I need to do, I need to take care of this thing. So I need to keep an eye on the Durbin-Watson statistics. So I'll show you that number there. So what is the interpretation here that we check for the, values here, and when we see that if there is some kind of, high or low Durbin-Watson values. So we need to, probably we need there are some issues with the model. So it requires certain adjustments so that we will have to work upon. So that is an important part here that we should take care. Now, what is the implication of this, autocorrelation thing that we are talking about? So if you are going with, high autocorrelated errors, so this will be leading to, if there's a positive autocorrelation, this will be leading to the underestimation of the standard error. Now, what is standard error? We are calculating a regression and we are calculating the values, but obviously the values will not be the perfect, predicted values. So there has to be something which will be, not exactly the value that we want to actually have. So that value will deviate from the, actual value. So that standard error captures that particular thing. And standard error plays a very important part in the forecasting, that it tells you what error you may have in your, what may be the level of errors in your forecasting terms. So if you are having high level of positive autocorrelation in your residual, the standard error will be underestimated, and the model fit, will be overestimated. And this, this is a very serious issue, because you are overestimating your model fitness and you're underestimating your standard error, and this will be a disaster. So it is very much important. Ideally, either we should, add some lags here, or we should transform the data, or, maybe some other way we need to look at the data so that we can develop a better model. So this is, these are very important things to keep in mind while going for the analysis. Another test which we will use is Gottfried test, so that we will discuss later. Let us just quickly see how do we get this Durbin-Watson test values here. So I'm going back to the eViews screen that I was using yesterday. And this is the same data that we were working on. I guess the same data. Let me just close it and we import the data that we were working on. So importing from the file, those who missed the session yesterday, they could also follow these steps. The file has been shared in the WhatsApp group yesterday only. So the same file I'm working on today. Tomorrow, if will be needed, I'll be sharing another file. If I cover the longitudinal kind of analysis, then I'll be needing a different file. So let us discuss the file that was shared yesterday. So this was the data. I'm just clicking directly, finishing the import here quickly. So this let's see, this is the data that we were working on. And yesterday we developed a model for small cap returns, depending on the mid cap returns and the Nifty returns. So we developed a regression model for that purpose. And how we did that? We go to the quick and we went to the estimate equation. This is what we did in the last few minutes of the session. And my dependent variable was a small cap returns. So I typed R underscore the way it has been written here. The same thing I have to type here. So R small cap 50, it is depending on, this is small cap 50 returns are depending on. I specified C here, that is constant. I want to get a value of intercept. So that is C. And then I defined R underscore mid cap 50 returns. Remember, this data is only for last 1 year. So it is 14th of March 2023 to 12th of March 2024. So this data covers that range only. So you could obviously get a larger frame of the data to get that thing. So we did this analysis yesterday and we just quickly, not worrying about other methods, we simply run the least square method. And this was the output that we received. Now, what happened normally, initial 2-3 years when I was using SPSS, I used to, showcase in this output to my students. I used to explain all those values here. And for some reasons, I don't know, I didn't, use these upper options over there. So you see there are a lot of information about the regression that is available here. So what we are talking about right now is residual. So we can click on the residual and we can see the kind of residuals we are getting here. So that all is there. So a lot of information is here. So we will explore that if time permits. Now, important thing right now, what we are discussing, the Durbin-Watson test, statistics here is coming out to be 1.93. So it is pretty close to 2. It is not perfect, but it is not serious also. So yes, there is some kind of, minor, very minor positive autocorrelation in the residual terms. But we need to deep dive. We need to check whether it is a significant issue or not. So that is, we can use some other test, but it is giving me an idea. It is not threatening. One time we were working on a model and we got Durbin-Watson number to be, 3.78. So that was something that we could get. There's a serious issue of negative autocorrelations in the residual errors. So that we could not proceed with. So we had to, refine the model and use some other methods which take care of that issue. So that way, if you are using a simple least square regression, which 90% of the time we do, so then in that case, we need to check for these values and make the interpretation. The important part is, if you are getting this Durbin-Watson statistics, at least tell what it is telling you. So we normally skip this kind of interpretation in the paper because we normally, what we do, most of us, will be capturing the regression equation from here. So most of us will be commenting on the probabilities of, values of individual independent variable significance like that. We will make the interpretation on R square. We normally make interpretation of the, regression model. And then if we are comparing different, models, then we can compare these criterion values. We'll discuss that in the session today. And then we normally ignore, normally I've seen people ignore the AIC, HQC criterion and then Durbin-Watson statistic. So we need to tell that if this value is appropriate, why not to comment on it? So we need to comment on it. Okay, tell me one thing before moving further. We have discussed about the Durbin-Watson. Can you quickly tell me what is the implication of this F value here, which is coming out to be 0.000? So anyone could answer in the chat box to me will be great. So what does this value tell? This F value, which is 0.000, the probability value of F statistic is 0.00. What does it tell? Does it make any conclusion about the model that we have run in the reviews, or
That
what is
indicate that there is hardly any residual variance.
there's hardly any
Almost zero variance.
zero
F is
value?
243 is it is F value. That means the variance, residual variance is minimum.
Okay. Anyone else would attempt the answer, or you can write in the chat box if you are comfortable writing in the chat box. That will be great. You can come on the mic as well. I don't mind.
Good morning. I realize if it is 0.00 doesn't make any sense at all. So whatever you are testing, it is coming to be negative. That's what I guess.
See, one thing that we must understand. Yeah, Lizzie, you're right. Diksha, it is too small value, but what does it tell? That's what I'm trying to make all of you understand. When we are running a regression, we need to check whether that regression model is significant or not. So Lizzie in the chat box has responded to me and writing that the model is significant, and that's what we exactly mean by it. So when we deploy or develop a regression model, we normally see whether this regression model is significant or not in overall. So there are 2-3 values which we always make yes, Vinayakji, this is the exact interpretation. The model is actually significant. So the regression model that we have developed here, we can say it in other words. What earlier this participant said, what might be meaning the same thing. But what we normally write here that the regression model that we have developed is a significant model. And why I'm saying that, because in this case, what you will make note of it. Just open a notepad and show you that thing. So what I'm doing here that let me just quickly make you understand the way we write about these information over here. So the equation that I'm getting here is just a minute. So the regression equation that we are getting here is this, and if I want to write a quick interpretation for this model, how will I actually proceed? So the very first thing is I will make an assumption here. I will make a hypothesis here. I'll say there is no significant dependency. There is no significant dependency of dependent variable. I'm just writing significant dependency of dependent variable. That is R small cap 50, on selected independent variables, on selected independent IVs. I'll just write it shortly. So IVs that we have taken is R mid cap 50, and we have taken another IV that is R Nifty 50. So these are the IVs that we have taken. This is the null hypothesis that we have made. The H not, is specified. So we have to specify H1, and that will be there is a significant dependency of dependent variable on the selected IVs. You could write it in a different way also. I'm just going with the most basic way of writing the hypothesis. So you can say the R Nifty, mid cap 50 and R Nifty 50 are significant predictor for the small cap 50 returns. That is a way of writing that was. So what we normally do after specifying the hypothesis, we normally go with the level of significance, and the level of significance in general, we normally keep it to 0.05. And that basically implies that you are 95% confident. So your confidence level is 95% and significance level that you're talking about is 95%. So that way it goes. And now the important part is you make interpretation. You have applied the test and then you are making an interpretation for that particular test that you have applied. And for that, we use the thumb rule, the p-value of the test. And here the p-value is ANOVA, and that is basically the F value. If the p-value of ANOVA is less than 0.05, then in that case, H0 will be rejected. Then H0 will be rejected. So here what I can see, in my case, what you will see, the p-value is basically what? P-value is coming out to be, p-value of this test is coming out to be 0.000. And this is less than, this. And hence I'll say H0 is rejected. And when I say H0 is rejected, that means H1 is being accepted. and that itself implies, which implies that there is significant dependency of what we are doing. But important thing that I made you understand yesterday also, this was the comment on the model significance. So what I have written here, this is the basically comment on model's significance. So this is very important thing that to understand what we are doing, that we are commenting on the significance of the model, whether this regression model is significant or not. So the F statistics is a value of ANOVA, and the p-value of that tells us that whether the model that we are using is a significant model or not. Another thing that we normally do while commenting these things, I'm just writing so that you can understand how you will write that in your paper. And these are the most important things. Comment on the R-square value. So when you say comment on the R-square value, so what we get here, the R-square value here in my analysis comes out to be 0.665064. Let's keep it short that way. And this means that, which implies that 66.50% of the variation in my dependent variable, that is small cap 50, is explained by the selected independent variable, which are two here, the selected independent variables. Now it also means, in other words, what I can say, in other words, the 33.50% of the variation in my dependent variable is not explained by the selected independent variable. So there are some other variables, which are explaining that thing. So we need to explore. So we have captured only 66.50% of the variation of the dependent variable in my model, and which is going to make sense. So that is the value. The maximum value of R-square will be 1. So because it is basically the square of correlation only, so the square of 1 will be 1. So that way it does. Yes, Diksha, this represents that we reject the null hypothesis in this analysis, and that means my model is actually significant. So while writing the interpretation, this is how you will normally comment, and this is the basic minimum interpretation that you normally mention in your regression output. I explained you one important thing also, which I did yesterday, and just again doing that. One of the respondents actually asked me to provide the way of writing the interpretation. That's why I thought to share this way. So another very important thing is you have to comment on significance of individual IVs. So comment on another thing that we will do, comment on significance of individual independent variables. So we can make comment on significant individual independent variables also. So here what we will do, as we did yesterday also, here what we will do, that we will look at these values. So the mid-cap 50 has a p-value of 0.000, but the Nifty 50 has a p-value of 0.21. So what you will do, you will just, you may specify hypothesis here. So you can specify the hypothesis here. But in short, because it's not the main interpretation, you can write in short, because in case of, and I'm talking about return of mid-cap 50, here my p-value is 0.000, which is less than level of significance, which is my alpha value. So this way you can simply signify this thing, because you have already commented on the model significance, but here you are commenting on the significance of individual I. So level of significance is 0.05 in general, if nothing is specified. So that which implies that this mid-cap 50 return, is a significant predictor. So this should be kept in the regression model because it is having significance in terms of predicting. You can also say that that small cap 50 returns are depending on mid cap 50 returns significantly. That can also be another line to mention the thing here. But if you will write the same line for returns of Nifty 50, the interpretation will change, because what happened here in Nifty 50, my p-value is slightly different. My p-value goes to 0.2152, and this time it is more than level of significance, and which implies that Nifty 50 is not So you can take the screenshots of these interpretation that I've written, is not a significant predictor. You can also say that mid-cap 50 returns are not significantly depending on the Nifty 50 returns. So it is not a good predictor. It is not a good predictor. We should not be using this in our regression model. So this is the way we normally write the interpretations for that thing. Now, what we have done by now, in the recent time, we have discussed about the Durbin-Watson. You can make a comment on it. So what is serial autocorrelation? What is the implication of having positive or negative autocorrelation of the residual term? And then in this model, we are finding it to be 2. So which tells it is slightly, if it goes down, so it is slightly positive, model, very mildly positive autocorrelation, but which is not a threat. So we will be checking with some other model that whether it is a significant serial autocorrelation or not. So we will be doing that. So I guess by this time, the things are by and large clear to you. If you have any query, you can put, concerns here, and then we'll move forward. So meanwhile, the next test, we normally apply for the same point. So if you want to check for the, higher order serial autocorrelation, and you want to check whether the, residuals, I hope residual term is clear to everyone. The difference in between, of the actual term and the forecasted term. So the residuals, if they are having higher order autocorrelation, that will be tested with the help of this Bush-Godfrey model test. So here the null hypothesis is that there is no higher order serial autocorrelation, and the alternate hypothesis will be that it is present there. So there is no significant higher order serial correlation. That is the null hypothesis, that it does not exist. And the alternate is that it does exist and it is significantly there. So we use some chi-square tests for that purpose. And decision rule is going to be again based on the p-value. You can compare the chi-square with the critical values using tables. Otherwise, you can directly use p-value that we normally do. So if the p-value is less than the significance level, that is a thumb rule, then we will say that we will be rejecting null hypothesis, and then we'll say there's a significant, higher order serial correlation. Now, the important thing is if you're comparing the critical values of the test, so there's a different way of interpreting that. So test statistics is more than critical value, then we also reject the null hypothesis. So if these things are found there, so certain adjustment in the lags and models will be required. That is what this test does. So let us do how it will be applied. So let us go back to the views here, and in this you click on the view, and in view you go to the residual statistics test. Residual diagnostics, and there are a lot many things in that part, but I'm covering right now the serial correlation LM test. So the moment you'll apply here, you just click here and it will ask you to lags. So by default, the most suitable lag will be identified. Let us continue with that as of now. And this is the Bush-Godfrey serial correlation LM test. And what we find here, the p-values, the probability value of chi-square is more than 0.05. So it has applied F test and its p-value is there. It has also applied observed R square and the chi-square value, p-value is there. So the chi-square p-value and the F p-value both are above 0.05. So if you can recall what we discussed, the null hypothesis was that there is no, high order serial autocorrelation, and the alternate hypothesis was that there is evidence of high order autocorrelation. Can you tell me here quickly, are we accepting or rejecting our null hypothesis? The p-values are above 0.05. So we are, yes, we are. Yes, we are accepting the null hypothesis, and that means there is no, higher order serial autocorrelation. So we don't have, we accept the null hypothesis, and that means the high order, serial autocorrelation does not exist in my data. So my residuals, my Durbin-Watson was 1.93, which was very near to 2. So it was not, threatening value. The threatening values will be like 0.5, 0.2, 3.8, 3.7, 3.6, as close to the extremes. The Durbin-Watson value will range from 0 to 4. If your value is coming out 2, you are safe. You don't have that issue of autocorrelations between the residual terms. So that is what you can check. I hope, normally, what happens. I have taught statistics, in various colleges. I don't get that subject to teach in my university, but at times as a visiting or some temporary assignments were there. So I'm just keen to teach statistics like any time. That's my though I'm a man of finance, but statistics is something which is very close to my heart. So that way, what we feel like that sometimes we teach regression, but we skip all these very important assumptions of the regression, how to test them, and what is the implication of them. So that is very much needed. So what we are learning by now, we talked about stationarity, we talked about the autocorrelation, serial correlation of the residual term. That's what we have discussed. It should not exist in the data if you're working and developing a least square regression. So the least square regression should assume, and it assumes that the autocorrelation of the residual term is not significant. Ideally, it is zero, and even if it is there, it should not be significant. So we are testing it, and in this data that we are testing it, this value is not significant, which is a good sign. So two things to remember, and then we'll move on to the next thing. Durbin-Watson value close to 2 is a good value, and if you are applying this Bush-Godfrey serial correlation LM test, then that value should be above 0.05. The p-value should be more than 0.05, so that you can say, yeah, there's no correlation issue of residual terms. You can just refer to this null hypothesis for that remembrance. Moving on, another very important aspect, and probably tomorrow I'll be able to cover that in detail. But today, let us introduce to the concept of heteroscedasticity. It's a difficult term to pronounce, but this is very much important, thing to understand. So the heteroscedasticity is basically what? That if you are having your data and you want to check whether your residual, let me just show you one thing. I'll explain you this with the help of one example on Excel, and then we'll understand the test which we can use for measuring the heteroscedasticity in our data or not. So I'll just make you understand the concept first, because it is a very widely used concept, and sometimes when we hear this term, some people get afraid of the spelling itself, and they sort of think it is very difficult concept, and it is not that difficult thing. So let me say that for some years I did some forecasting kind of thing, and this yearly values were there, and I had the actual values of I just had the actual values of my data, and in actual values, my values were like let's say, I'm just mentioning few values on my own. So the actual value was 100, 105, and some random numbers I'm just picking over there. So we got these actual values here, and we developed a regression model, and that allows us to calculate some forecasts for these values, and we calculated the forecast over here. So the forecasting we did, and the forecasting was something like this that we were getting. So we got these forecasted values, and these are the forecasted values that we got using our regression model. So in this case, what happened here, if you see the residual term here or the error term here. So the residual term is basically actual values minus the forecasted values. And deliberately I've kept a pattern here. The residuals, are 2 or -2 or 2 -2 randomly like that. So when you square them, so this is the squared error or the squared residual. So when you say the squared error or squared residual, so you will be able to square these numbers. So this is residual or error is one and the same thing. So there's no difference in that. So you just square these numbers, and when you square these numbers, you find they are constant. So we had the actual values, we did the forecasting. I'm skipping that part here in the explanation because I want to make you understand this line. My focus of explanation in this Excel file is in this F column. So we had the actual values, we did the forecasting, we got the forecasted values, and we calculated the residuals of each actual value, and the residuals were squared later, and these are the squared error. And what we see here is a perfect constant squared error. So we are having a squared error which is very much constant. It is not deviating like anything. So this way, when you have this kind of data, if you have this kind of data, this is known as the homoscedasticity. So this is where the squared variances are actually constant and they are not deviating too much. So this is known as the homoscedasticity. So we have this data set there, which is the homoscedasticity. If I just use the same data set here, and if I want to run, if I want to make you understand some other concept of heteroscedasticity, so what will be the case here that I'll just explain you. So if your actual values are the same, but your forecasted values were like this. So you had some random, numbers I'm talking about here. So 115, we had the actual value, but my forecast was 99. And 117 was the actual value, but my forecast was, let's say 158. And 98 was the actual value, my forecast was 109 and so on. So we did that. So now suddenly what we are seeing is, suddenly this is the case where the squared error is perfectly constant. It will not happen, let me tell you. The perfect homoscedasticity cannot exist in the data. There has to be some variation. So 4 may be there, 5 may be there, 8 may be there, 64 may be there. So then there'll be some deviation for sure. Why we are squaring? Just to improve on that signs part. We are ignoring the signs of the deviation. We are just seeing the squared error here. But when you see the squared error here, so the squared error is ranging from 9 to 1681. And this could go anywhere. This could go anywhere. If I say when I had the actual value, my forecasted value was 250, and it was a huge squared error over there. So now suddenly what you see that your error term, which is squared, is not consistent. So though it's a very lame explanation that I'm giving you right now, we go and check on very further details. We check for with the variance term of the squared error. So I'm not covering that part. But just to give you basic understanding that when your squared error is there and it is very much constant, then this model, this homoscedasticity is a prerequisite for least square method. So then you should be using least square method, because in that case, you are good to go with the least square method, because least square method assumes that whatever squared errors we are going to get, they are going to be having a consistent, variance. But if you are having this heteroscedasticity kind of thing, then least square method cannot be used. This should not be used. You have to somehow refer to some other advanced models like Arch or Gauge or P-Gauge or something like that. So we normally go with that autoregressive conditional heteroscedasticity kind of thing. So this is called Arch. So you will be using a different kind of model over there, and which will be needed there. So this is the point to remember. I hope this brings a basic understanding of the term here. So what we are doing, so when you are having homoscedasticity in your data, you will be using least square method. But if you are having heteroscedasticity in your data, you should not be using least square method, because it's not a method which is meant to handle the variables which are having the problem of heteroscedasticity. I hope that heteroscedasticity concept is somehow clear to everyone, and I'm explaining it from that perspective that we are learning it for the first time. So I told you there's a squared error, will be further seen on the basis of variances and other things, other statistical things. I'm just giving you brief perspective in layman language how to make sense of these terms. So this is the point where you have to decide whether your data is suffering from the problem of heteroscedasticity or not. And if it is suffering from heteroscedasticity and you are applying a least square regression, which we have done in our case, it will be not appropriate. So we need to check that condition as well. And if it is existing there, do not worry. We have models, we have regression parameters, which can handle this kind of issue and this kind of problem. So that's why, I said yesterday, it is something, in e-views, if you will ask me that if you know 100 on 100, I'll say no. I'll definitely honestly say no, because there's so many tests, there's so many things, you keep finding, you keep learning. So that's the beauty of this, econometric kind of thing. So we come back to the e-views part. Let us discuss this slide first. So what we have understood that heteroscedasticity is an issue. So what we are doing to test for the heteroscedasticity in the residuals of a time series model, we use this Bush-Wagon test. We'll also have white test for that same purpose. We'll be using that as well. So now regress, what it does, it regresses the squared residuals on the original model's independent variable to detect any linear relationship between them. So, it's a statistical term, but let me make you understand in a simple thing. It basically types of running a regression model where you are, running you're taking one variable as your residual errors, squared residual errors, and then you are taking the independent variable. And you try to see whether if there exists any kind of linear relationship between them. And chi-square, is used for that purpose. So hypothesis here, the H naught will be homoscedasticity and H1 will be heteroscedasticity. So if your H naught is accepted here, you will say your data is having the issue of is not having the issue of heteroscedasticity. It is the homoscedastic data. We can run the normal least square regression. But if H naught will be rejected, then the data will be, called having an issue of heteroscedasticity, where the variance, the error term is depending on some independent variable. Then you have to look for some other model, adjusting your refinement of the model to get a better prediction model. So that is how we normally proceed. So let us quickly see how we will run it. So let us come back to eViews itself. And in eViews, you will go to this, in the regression output only, we are doing all this. So you go to the eViews here, and you go to this, residual diagnostic, and you have a heteroscedasticity test over here. And here you can see this Bush-Pagan test is there mentioned with the Godfrey description. You just click OK here, and you'll be finding the issue here. So what we find here, that p-values that we are getting here in heteroscedasticity test, they are found to be significant, because the p-value is less than 0.05. That means our data was not having an issue of the correlation of the residuals. Autocorrelation of the residuals was not an issue. So that on that parameter, we are good to go. But in this thing, and this happens in the capital market or any, econometric data, which is very dynamic and in range and nature. So here, what we are finding, there is, an element of heteroscedasticity in my data, because the p-value is 0.000, which is less than 0.05. And when I say less than 0.05, I mean to reject my null hypothesis. And the null hypothesis was homoscedasticity. So homoscedasticity has been, rejected. That implies that my data is suffering and having a significant, a point of the heteroscedasticity. So I need to probably somehow deep dive and see what can I do to deal with this issue of heteroscedasticity. I hope that explanation is clear to everyone. Another test that we can apply for the same thing is white test. And white test.
So there is one question.
Yes.
That as this data is a range for a 1 year.
Yeah.
So if suppose we have a big range of a data, like suppose 5 year, 10 year. So is this also affect, or in every cases, this value must be same, or that will let us know that this is heteroscedastic or not?
See, normally, what is the case? Duration of the data is one issue. We are having only 1 year data, and that's a logical understanding. The pattern may not be a robust and persistent pattern. So because we are only considering, 240, 250 observations given from a year. So your question is a valid question. But, what will be a case? Let us assume that we are going for the data of last 5 years of the market. Will be having around 1200 observations. The larger observations, the larger deviations, and the picture, slightly looks maybe different. But what is important, what model we are developing, the model that we are using, a forecasting model. And in forecasting model, we have to check for the stationarity things. We have to check for the, serial autocorrelation. We have to check for the, heteroscedasticity as well. The reason of using this test is, even in the larger sample size, is that if my, residual error terms are not consistent over the duration, and the larger the duration, that chance even may go up. It may average out, or it may be having larger variance of the, squared residuals. So that way, it is always good to check whether we are having this issue in our data of heteroscedasticity. And if we have that issue persisting in our data, we have dedicated models to deal with the projection, when the data is having the issue of forecast of this thing. So what we will do, it's a very simple thing. I'll just give you a brief understanding here that when we'll be applying arch model, let's say simple arch model for this. What arch model does? Arch model takes this, squared error residual as an input for the forecast. So when we have a residual error, which is significantly, having a linear relationship with my independent variable, why not to add it in my regression model using a variance equation? So in Arch, you will be having a mean equation, and along with that, you will be having a variance equation. So indirectly, what you are doing, you are ideally the error should not happen. So our life should be error free. But if my life is full of errors, why can't I use those error situations to predict my future, things? So whenever I take my decision, I know what is the ideal course of decision as per my understanding that I have. But let me use the errors equation to add on that experience to my forecasting. That last time I did the same thing, but I found this thing which was not going correct. Let me use that as an input for my forecasting or decision making in the next step. So this is that beauty of these statistics. It allows you to use squared residuals. If least square method is a wonderfully robust method. Let me tell you. I normally play one game in my class. I give them the problem like this, and if I say, okay, you are having this data, you develop a regression model, and it's a very simple thing. If I develop a regression model, I can simply calculate intercept and slopes over here. So if I say, okay, I'm calculating intercept here, so these are my y's, and these are my x's. I normally play this game, just to make them understand how robust this mechanism is. So this is the value of a in my data, and if I calculate b here, so I can calculate slope. I can use a data analysis package, but I'm just telling you the simple thing that I want to make them understand. So if I tell them, okay, this is the known y's, and then you have known x, and you just enter here. So this is the value. So now the regression that we will be running, will be based on these a plus b. And I tell them, you calculate squared error using these a and b equation combinations, and then you try any set of a and b and try to beat that sum of squared error. And it is amazingly strong, method, because this is the least square method, because the total of the squared error with these values of a and b will be the least, and it does that, in a span. So that is the beauty of the method. But to answer your query, yes, when you are working on the larger data set also, you should be testing for heteroscedasticity, and if it exists, use a better model which addresses that issue of heteroscedasticity. We have another method here, which we call white test here. And white test is, another very important method here, which we use for checking the stationarity. So in white test, why it is basically used here, because it is basically more robust method in terms of, because it can observe and capture both conditional and unconditional heteroscedasticity. The earlier test that we have discussed for that purpose, Blution-Pagan test, and it captures the basic heteroscedasticity. But if you're talking about conditional and unconditional heteroscedasticity, the white test is a widely used test for that purpose. However, the interpretation is very similar. The null hypothesis is again the homoscedasticity, and the alternate hypothesis is the heteroscedasticity. If null is rejected, then there is an issue of heteroscedasticity, as we have in the previous test. So that way it is very simple. But the only thing is, by conducting this white test, you'll be able to determine whether there is a systematic pattern of variability in the residuals, and if that is there, that violates the assumption of the least square method. So this is very much important. Now, important thing is, why we are all doing this. We just want to make sure that the coefficients that we are developing are reliable. The accuracy of the standard error that we are getting, is there. So that is the purpose of doing this. Now, conditional and unconditional, heteroscedasticity is something like which conditional means that squared error term is having a relationship with the independent variable, and unconditional is not capturing that way. It is just capturing the squared residual term on its own, how much it is fluctuating. So the conditional one and the unconditional one both are being captured in the white test. So you can use the white test for that purpose. Let me just show you that quickly. So if you go to the residual diagnostic, and you go to the heteroscedasticity test, and here you have the option of white test. So you can just click here and check that number. Again, this will come very similar. It will be very similar to what we have got in the previous test, and these values are also significant, less than 0.05. That means the data is suffering from the issue of heteroscedasticity. So here, developing on this 1 year data set, developing the regression model based on least square method will not be a good idea. We need to probably refine our model, change the lags, or look for some better techniques for that purpose if you want to address the issue of heteroscedasticity. Any point of confusion by this point, you can ask me. Otherwise, I'll cover one more category of test and then we'll conclude the session for today. So we have covered white test. Now, one more thing that I want to cover for today, if time will permit, I'll cover the normality part as well. These are the prerequisites, and then tomorrow we'll be doing the arch, gauge, causality, granular, Johnson integration, and if time will permit, then panel data and moderation kind of thing as well. So the test of model goodness of fit, there are two tests of model of goodness of fit. One I've already explained to you while writing the interpretation there. So the one is adjusted R square. So when I say adjusted R square, so see, I've explained you the R square value. I've not explained you the adjusted R square. I'll show you where that value is. So you have the, when you were having the stats of your regression model, this was the R square value. The R square value was 0.665. And the adjusted R square value is 0.662. Now, how does adjusted R square, value play a very important role? I asked my professor, I remember way back, I'm telling you the story of, my PhD days. So approximately 16, 17 years back. So we learned this method of regression from SPSS. SPSS was getting popular in its very early days. So I attended a workshop and I just asked him, sir, what is the implication of this, R square and adjusted R square value? How do we make interpretation of it? R square was understood that, okay, this tells me that this much of percentage of the variation of the dependent variable is explained by the selected independent variable. That was clear to me. But what was the relevance of having adjusted R square? So that professor was a very good professor and he started playing a game with me. And he said, okay, dear, you just go and collect the data on 3 economic variables. You run the regression analysis and you come up with the data and interpretations of that. So it was an easy task. I just retrieved the data from the portal he suggested me, and I retrieved the value of R square and adjusted R square. Day 1, my R square was 0.42 something, and adjusted R square was near about that value. So I said, sir, this is the output. He said, okay, don't you want to increase the value of R square? I mean, yes, it will be great if I can increase. So we went with another addition of the independent variable. He said, okay, add this variable, you'll be getting a better R square. And that happened. I added another independent variable, R square went to 0.56. And this exercise kept on, happening every day. So I used to go to him, he used to tell me another variable, and the R square value used to go up by a certain percentage. One day I was getting a little impatient. I said, sir, I just asked you, what is the meaning of adjusted R square? You are making me come to your office every day for that simple question. So he said, today, what is your R square? I said, R square has gone up by again 2%. And he said, look at the value of adjusted R square. What happened to adjusted R square? And that day, it was the first day when I was doing this for 4 days. The 4th day, when I was adding the independent variable, the adjusted R square dips down. So that was a point, and I looked at the significance value of that particular independent variable. I found that that independence variable was not significant. I was not that sharp as I am today, obviously. I was learning the statistics and basics, and he was my profound guide for that thing. So I understood and I captured it. I said, okay, and when I added a non-significant independent variable today, R square still went up by 2%, but the adjusted R square actually dipped down by a particular value. So when you add independent variable, R square value tends to increase every time, whether it is significant or not. In 99% cases, that will happen when you will add independent variable in your regression, the R square value will increase. But the addition of non-significant independent variable will bring this adjusted R square value down. So whenever you are adding, independent variables to increase your R square, keep an eye on the adjusted R square and keep an eye on the probability value of individual independent variable. If that variable is not significant, there's a likeliness that when you add that IV in the model, that adjusted R square will go down. So that is a point that I learned. And I normally quote this story. It takes 2-3 minutes, but I quote this story whenever I explain the adjusted R square, because this is how I learned the value. So this is a practical derivation of that adding IVs. Normally what happens as a novice researcher, we keep on adding IVs like anything. And we are happy to increase R square. And one day, in one of my papers in my early days, I achieved an R square value of 0.95, and I was so happy. And later on, one professor, explained me the harm of having such a high R square value. So you are taking something which is autocorrelated or always, going to be highly correlated. So there's no fun doing that thing. And they were very much complementing in nature. So there's no fun estimating a variable who has a mirror variable somewhere. So what I was doing, I was taking the trade quantity or some turnover data of the Nifty contracts or value of the transaction, something, and I just forecasted a Nifty on that basis. So it is a very highly correlated value. They'll be having very high R square value. So there's no fun doing that. So we must be careful while developing the R square value, and this is one of the things that I hope you could understand what the values are. One more thing for the day, we have a time, so 2-3 minutes. So there's a Akaike information criterion and there's a Bayesian information criterion. And what they do, they are basically used for selecting the best model. So if you see in the output here of the eViews, so in the output of eViews, you see there's the value of AIC and there's Schwarz criterion, which is also known as Bayesian information criterion. So Bayesian information criterion is also known as the Schwarz criterion. And we do have this HQ criterion, which is again the same thing. So if you are developing various models for predicting the same dependent variable, what you will look at, you've developed like 5 different models and you want to choose one particular model for that purpose because dependent variable is the same. You will pick, the minimum values, ignore the negative sign. You just pick the minimum value, like 7.4 is there, Akaike information criterion. The another model you have 7.3, ignore the negative sign, take the absolute value. And if that second model is having AIC value of 7.3, you go with the 7.3 model because that's a better model. That will have a better R square, that will have a better model fitness. Another thing that is mentioned here, sometimes what happens, we normally make very complicated model. So model complexity is one thing and the goodness of fit is another thing. So the complex model is there and the goodness of fit model is also there. Goodness of fit is very, very much needed. What we were doing in the Amos. So the goodness of fit and complexity, has to be balanced. So these criterions are actually doing that. So if you are having multiple models, then this value again becomes very important. You can actually look at the minimum of these values and select the model with the minimum of these values, lowest of these values, and that is what is preferred. So that basically help you balancing between the model complexity and the goodness of it. That is the important purpose. Last for the day is the test for normality, and that we use normally JB test, that is Jar-Cube-Bela test, and that can be used for seeing whether your data is normally distributed or not. And it's a very simple thing. See, you have done the analysis. If your data is not normally distributed, you probably will not be able to generalize your statement. So if you are working on a data and the data is not normally distributed, you'll not be able to generalize your interpretations over there. You should not be generalizing on the basis of 1 year data for sure. What I'm doing is a demo class here. It's not anything, this is not whatever I've said right now in my, explanation was not carrying any research significance. It was a demo data just to make you understand how to run the analysis things and make some interpretations, what values we are getting. So if you are having a larger data set, proper study frame, then you want to check for the normality because you want to say my data is normally distributed. Whatever I'm saying is, following a Gaussian distribution, it has the power. It can be generalized to the large, things. So larger data sets can be applied on that thing. Small data sets may have the issue of normality, but the larger data sets will not have that issue for sure. So you can use this Jar-Cube-Bela test for checking the normality here. So how you will do that? So if you just click here, view, and just a minute, you will go on the residual, not on residual.
Sir, can you tell the significance of man-Whitney test?
Man-Whitney test. Man-Whitney test, is a test which is a non-parametric in nature, and you want to compare two, independent samples, and both the independent samples are suffering from the issue of the, normality. So both the samples data that we have is not normally distributed. So when your data is not normally distributed, you will be, applying this test. So that way, we normally apply man-Whitney test to compare means of two independent samples which are not normally distributed, because man-Whitney is a substitute, non-parametric substitute of the two samples independent simplicity test. So that is the point. I have got one more query. When we are collecting data from multiple sources in panel regression, data may not be normally distributed. How will we address that issue? We probably either there are one possible way of transforming the data. So sometimes the log transformation works, sometimes we make them log returns another way. So the transformation normally, first order transformation or the second order transformation will make the data normally distributed. So that is what we can do. And once we'll be making a model for transformed series, we'll be forecasting the transformed series, then we'll be able to, get it back, transformed while making the prediction. That's the way of dealing with the non-normal probabilities things here. So I'll be discussing about other things, causality grinder and this normality test, I'll be sharing that interpretation tomorrow. I guess time is already over. So that's it for today. If you have any queries from the today's discussion, you can ask.
Sir, I asked you about the eigenvalue, EIGN.
That, ma'am, I'll be covering Arch model tomorrow. So that
Yes, because I run that model, but I'm unable to understand why these values are used.
I'll explain that tomorrow. Reserve that question for tomorrow. The first question, I'll be discuss those things. I'll be sharing that.
Okay, sir.
Thank you so much. Some moderating effect in random effect panel regression. I'll just note it down. If time will permit, I'll definitely quickly give an overview on that. So I'm just noting it down with my points to be covered. So I've noted down in my notebook. So definitely the eigenvalues in this will be trying to cover that. Thank you. So I think we are done for the day. Thank you for your participation, and we'll be discussing the remaining part of this FDP in the last day of the session on the Monday.
Thank you, sir. I hope everybody understood. As we draw the curtains on today's session, I extend my sincere gratitude to all the participants for your unwavering dedication and active engagement throughout the day. Special thanks to Dr. Angit Saxena for his invaluable insights. Let us carry forward the knowledge gained and continue to inspire excellence in our academic endeavor. We eagerly await the 7th day session, which is beginning next Monday. Participants, we will reconvene at 11 a.m. That is on next Monday, coming Monday for the next session. Thank you all. Thank you, everyone. Thank you, sir. I remind. Thank you, ma'am. Okay, we are going to end the session.
Yes, we'll end the session now. Thank you so much, sir. Last day, Monday, whatever the queries are there, please resolve those queries.